Hi everyone, this is Dr. Baby Shalini, Associate Professor, Department of ECE, Rohini College of Engineering and Technology. In this video, we are going to see about small signal model of a diode. Let us consider a simple circuit of diode under forward biased condition with a forward biased voltage VDD which is applied through a resistor R. So this is said to be forward biased because the positive of VDD is connected to the positive end of diode and the negative end of VDD is connected to the negative of the diode. So this is said to be forward biased. So this circuit is approximated as shown in this figure. So here the difference is the diode D is replaced by its corresponding voltage 0.7. So for a silicon diode the built-in potential is 0.7 volt, so that we are replacing the diode with the built-in potential 0.7. So now we are going to find what is the current ID through this resistance. So current I is equal to voltage by resistance. Here we are having the difference between two voltages VDD and 0.7. So ID can be written as VDD minus 0.7 dividing by R. So now let us consider the situation where the supply voltage VDD is increased by a small amount said to be del VDD, and correspondingly the diode current ID get increased by a small amount del ID, and in turn the diode voltage VD gets increased by a small amount del VD. So this model is said to be small signal model of diode because we are considering a small incremental values across all the elements. So for the above circuit we will get the performance curve like this. So this is the IV characteristics curve of a diode. So the IV characteristic curve is drawn between the voltage V and the current I. So V is represented in x-axis and current I is represented in the y-axis. So just look at carefully. So we know that the VI characteristics of a diode is a exponentially increasing curve, so that we are having the black curve as a exponentially increasing curve. Now let us consider for the built-in potential 0.7 we are having the corresponding ID current as 1. So the intersecting point of this one with respect to the exponential increasing current is said to be the bias point Q. So now let us consider we are varying the voltage to a small amount, so that from 0.7 below and above 0.7 we are having a small incremental voltage del VDD. So corresponding to this voltage we are having a small incremental current ID which is represented in the x-axis. So now just we are considering a tangential line that is passed through the bias point Q. So let us consider the condition where del VDD, del ID and del VD are initially considered as 0 volts. So when these values are 0, we are getting a DC bias point that is represented by Q. Now let us going to find the change in diode current ID with respect to the change in diode voltage VD at the Q point. So we are going to find dou ID by dou VD ratio. So we know that the diode current ID is equal to IS into e power VD by VT, where IS is the reverse saturation current and VD is the diode voltage and VT is the thermal voltage. So now we are going to differentiate this equation with respect to VD. So while differentiating, IS is a constant and the differentiation of e power VD by VT is e power VD by VT into 1 by VT. So when rearranging this equation, we will get IS into e power VD by VT dividing by VT. So now look at the numerator term, which is nothing but the diode current ID. So the numerator is replaced by the diode current ID dividing by VT. So now this is the ratio of current to voltage. So we know that ratio of voltage to current is resistance, but here we are having I to V ratio, which is reciprocal of resistance, otherwise called as conductance. So the unit of conductance is mho, and it is the ratio reciprocal of resistance, so that it is represented by the diode resistance 1 by Rd, and its units is 1 by ohm. So now the total diode current is the addition of DC current Id plus the small signal AC current Id. Similarly, we will get the total diode voltage Vd, which is equal to the DC or bias voltage Vd plus the small signal voltage Vd. And the small signal resistance is represented as Rd is equal to ratio of diode voltage Vd dividing by the diode current Id. So, as a consolidation, we can come to a conclusion that the first circuit represents a DC bias point. So, in this case, only the DC voltage VDD is considered across the diode. And while considering the small signal analysis, we are going to make a small increments in VDD, ID and VD. So, which are represented by del values. And when we are adding these two circuits, we will get a complete small signal model as represented in the right hand side diagram.